Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Now let's take a look at one of the cornerstone theorems in group theory, along with Lagrange's theorem and Cauchy's theorem is Cauchy's theorem. Cauchy's theorem is quite easy to state. If P is a prime dividing the order of a finite group G, then P has at least P minus 1 elements of order P. And of course this implies that G will have at least one subgroup of order P. This isn't quite how you usually see the statement of Cauchy's theorem. Usually it'll simply say that if P is a prime dividing the order of the group G, then G has an element of order P. But in fact, the proof that we will give shows that there's at least P minus 1 such elements. Cauchy's theorem has a rather colorful history, beginning with its discovery by Cauchy in 1845. It was the main conclusion of a 101-page paper. And here's a quotation from the abstract of an article on the history of Cauchy's theorem by Mio. I have references here both to Cauchy's original paper and to Mio's paper. It's in the book. Mio says, the initial proof by Cauchy, however, was unprecedented in its complex computations involving permutational group theory and contained an egregious error. A direct inspiration to Cauchy's theorem, Cauchy's theorem was reworked by Dedekind, Frobenius, Jordan, and Mackay in ever more natural, concise terms. The proof I'm going to give is essentially Mackay's proof. The ideas are Mackay's, but I've done some rewriting just to change the exposition a bit. Mackay's paper was published, or Mackay's proof was published in 1959, so it's well over 100 years after Cauchy's original paper. So here is the theorem. Let G be a finite group, let P be a prime dividing the order of G, then G has at least P minus 1 elements of order P. Now the key to the proof is to examine this set here, X, of all ordered p-tuples of elements of G where the product of the components is equal to 1. This set is non-empty because the p-tuple with all 1s belongs to X. And note also that it's pretty easy to find the size of X because we can assign any values we want to the components A1 through AP minus 1. And then AP is uniquely determined by the fact that the product has to be 1. So the size of X is the order of G raised to the P minus 1 power. Now, we'll refer to a p-tuple, all of whose coordinates are the same as a constant p-tuple. If we can find a constant p-tuple other than the p-tuple with all 1s, we've found an element of exponent P, because the product of A with itself P times A to the pth power is 1, and therefore of order P, because P is a prime. Note that a p-tuple, such as this, is constant if and only if a rotation one position clockwise. So actually to the right, it would probably be a better way to say it, with wraparound fixes the p-tuple. In other words, doesn't change it. So this is the clockwise rotation. A to the p comes to the front. So x is constant if these two p-tuples are equal, because then a1 here is equal to, well, let's see, a1 here is equal to a2, a2 is equal to a3, a3 is equal to a4, and so on. They're all equal. So let's denote this rotation by row. So row sends a1 through ap to ap followed by a1 through ap minus 1. And then x is constant if and only if row x equals x. Now row to the k, x, is a k-fold clockwise rotation with wraparound. And since row to the p brings us back to the original, we've rotated p times, that's the identity. So a complete set of clockwise rotations is given by the cyclic group generated by row, which has order p. Counterclockwise rotations can be achieved using clockwise rotations. So, for example, a counterclockwise rotation one click is row inverse, but that's equal to row to the p minus 1. So in fact, this cyclic group generated by row gives us all rotations of the p-tuples, clockwise and counterclockwise. Now we define a binary relation on x by saying the two p-tuples x and y are related if one can be obtained from the other by a rotation in this cyclic group. And this is easily seen to be an equivalence relation on x, and so produces a partition of x into equivalence classes. The equivalence class containing x is the collection of all rotated versions of x. So it's a set of all row to the kx, where k is in this range. This is an equivalence relation. It's reflexive because the identity rotation means that every p-tuple is related to itself. It's symmetric precisely because I went through the trouble of showing that counterclockwise rotations belong here as well. So you can go in either direction in rotating, and it's transitive. That's pretty straightforward. Now, a p-tuple x is a constant p-tuple, that is to say row of x equals x, if and only x lies in an equivalence class all by itself, an equivalence class of size 1. Because that means that all rotations of x are simply x itself. Therefore, the proof of this theorem will be complete if we can show that there are at least p one-element equivalence classes. We need p because one of the one-element equivalence classes is the one that contains this all-one p-tuple, and that's of no value to us. So we're left with at least p minus 1 one-element equivalence classes. Those correspond to the p minus 1 elements of order p. So we need to get a handle on the sizes of the equivalence classes. And for this purpose, we look at the set fix x of all rotations that fix x. So rho to the k is in fix x if and only if rho to the k x equals x. This sort of analysis we're going to encounter again a bit more formally when we talk about group actions. Fix x is a subgroup of this cyclic group because the product, which is composition, of two rotations that fix x will also fix x. So it's closed under product. So Lagrange's theorem tells us that the order of fix x divides the order of the group, which is P. And so fix x either has order 1 or order P. This is a critical use of the fact that P is prime. This whole proof would fall apart if P wasn't prime. Another way to say this is that every either every rotation in the group fixes x or only the identity fixes x. It's all or nothing. And by nothing I mean just the identity. That's always going to fix x. And this is again the consequence of the fact that P is prime. Now if fix x is equal to 1, then each of these p tuples rho to the k x is distinct. So this is telling us that the only thing that fixes x is the identity. But if you have rho to the kx equals rho to the jx, k and j are between 0 and p, and we can assume k is bigger than j, then that means that rho to the k minus j fixes x. This is still in this range, 0 to actually p minus 1. And so this must be the identity, which means k must equal j. So when fix x is trivial, has order 1, the equivalence class for x consists of all of the rotations. They're all distinct. And that has size p. On the other hand, if only the identity fixes x, so the order of fix x is p, then every member of the group generated by rho fixes x. And so the equivalence class containing x just contains x. It's a one-element equivalence class. So all of the equivalence classes in this partition of x either have size 1 or size p. So we can suppose that there are B equivalence classes of size 1 and C equivalence classes of size p. Then, because the equivalence classes form a partition of x, the size of x is B plus Cp. Also, because we know there is at least one element equivalence class, we know that B is bigger than or equal to 1. B is not 0. On the other hand, we already have a formula for the size of x, this one, and this is divisible by p because p divides the order of g. Therefore, this has to be divisible by p. Cp is certainly divisible by p, therefore b has to be divisible by p. So the number of equivalence classes of size 1, those correspond to the constant p tuples, is divisible by p. So it's bigger than or equal to p. And that's what we were trying to prove. So that, in essence, is the proof of Mackay, coming well over 100 years after Cauchy's original proof. Cauchy's theorem is extremely powerful. And let me give you just sort of a vague idea now one reason why that's true, and we'll go into more detail on it in a little bit. Suppose that we have a non-trivial group G of order n, and suppose that a prime P divides n. Then Cauchy's theorem tells us that G has a subgroup, which I'll call HP, of order P. Suppose further that this subgroup is normal in G. Now, while normal subgroups are sometimes difficult to come by, if G is abelian, all the subgroups are normal, so this would cover that case of abelian groups. But it covers many other cases as well. Then the quotient group, G mod HP, has order n over P, which is less than n. So this gives us the idea that we may be able to prove certain results about finite groups using induction on the order of the group. Because the inductive hypothesis will be, we can apply it to the quotient group. So if the results are amenable, if the properties we're looking at are amenable to translation up from G mod HP to G, this might work. Now I know that's kind of vague, but when we do, we're going to use it twice, you'll see how it works. Okay. First thing, however, though, is I want to discuss P groups, because those will be extremely important both to us now and for a good portion of the rest of the course. Elements of prime order and prime power order do play a fundamental role in understanding the structure of finite groups. And so that's, in fact, a main reason why Cauchy's theorem is such a cornerstone theorem, so important. So here's some terminology related to these ideas. Let G be a group and let P be a prime. An element A in G is called a P element if its order is a positive power of P. It doesn't have to be P. It could be a power of P. G is a P group if every non-identity element of G is a P element. So every non-identity element of G has order positive power of P. A non-trivial subgroup, H of G, is called a P subgroup if it's a P group in its own right. So all of its elements have order a positive power of P. Now, first item of business. Some authors, many authors, maybe too many authors, define a finite P group differently. They say that a finite group G is a P group if G has order a power of P. Don't mention the elements. It's the order of the group is a power of P. Well, this is equivalent to our definition for finite groups. But our definition, which by the way is not my own, it's a common definition as well, has the advantage that it applies to infinite groups as well as finite groups. To see that the two definitions of P group are equivalent, at least for finite groups, we can appeal to two cornerstone theorems, Lagrange's theorem and Cauchy's theorem. And the proof I have here is just 3 lines long, so I would like you to see if you can construct the proof yourself. It's be good practice for you. So I'm not going to discuss it explicitly. But I want to move on to something quite interesting, actually, and that is the subject of Lagrangian groups. So suppose G is a finite group. Now we've seen that the converse of Lagrange's theorem, which is the statement that for every positive integer d dividing the order of the group, there is a subgroup of order d, fails. And the example we looked at is the alternating group, A4. We showed earlier in the course that it has order 12, but there are no subgroups of order 6. On the other hand, there are certain classes of groups for which the converse of Lagrange's theorem does hold. So that's enough to deserve a definition here. A finite group G is Lagrangian. It's also known in the literature as a CLT group, converse of Lagrange's theorem, if it has the property that if D is a positive divisor of the order of the group, then the group has a subgroup of that order D. So A4 is not a Lagrangian group. But we have seen that every finite cyclic group is Lagrangian. In fact, if D divides the order of a finite cyclic group, there's a unique subgroup of order D in that group. Now, two of the most important classes of Lagrangian groups are the finite abelian groups, which contains the finite cyclic groups, and the P groups. This one's maybe a little more remarkable because it's not; these are not necessarily abelian. Before I prove these two facts, it's worth mentioning that the question of exactly which groups are Lagrangian is still open. We don't know. It's a subject of current research. We don't know exactly which groups are Lagrangian. There is a result, for example, that if the center of a group is rather large, in particular if the index of the center in G is less than 12, then G is Lagrangian. These groups are, I guess, in some vague sense, mostly abelian because they have large centers. But there's a lot of other results along these lines, and they involve concepts that we haven't discussed and won't discuss, such as nilpotence and supersolvability and other things. So we're going to have to end this conversation here. But let's prove that finite abelian groups and P groups are, in fact, Lagrangian. And we'll use the technique that I mentioned earlier of induction that when we talked about how powerful Cauchy's theorem was. So, first, finite abelian groups. Suppose G is a non-trivial abelian group of order n. If P is a prime dividing n, then Cauchy's theorem tells us that G has a subgroup, which I'll call HP, of order P. And the quotient group, G mod HP, is also a finite abelian group, but its order is n over P, which is less than n. So we are primed now to use induction to prove this result, that every finite abelian group is Lagrangian. But the question is, while we can assume then under the inductive hypothesis that the quotient group is Lagrangian, how do we relate the subgroups of the quotient group to the subgroups of G? Because we're trying to show that G has subgroups of all possible orders. We know that the quotient group does, but how does that relate to the subgroups of G? Well, the answer is given in this theorem. This actually is going to come up again later when we talk about the famous correspondence theorem of group theory. If you took my linear algebra lectures, then you know about the correspondence theorem for vector spaces. there's an analog for groups, and it relates directly to this issue. At least part of it does. Let N be a normal subgroup of a group G, then every subgroup S of G mod N has the form H mod N for a unique subgroup H of G. And of course H will contain N, otherwise this wouldn't be well defined here. In addition, if H mod N is normal in G mod N, so if the subgroup S is normal in G mod N, then H is normal in G. Okay, how does the proof go? Well, first we need to show that H exists. Now the subgroup S of the quotient group is of course a set of cosets of N in G. And because S is a subgroup, this set of cosets is closed under products and inverses and contains the identity coset N. So let us consider the union of all of these cosets. We have to pass from cosets to elements of the group. This seems like one reasonable way to do it. Remember, cosets are just subsets of G, so take their union. Now there's one key property that this set here has that will be enough to finish the proof. An element, little h, is in H if and only if it's in one of these cosets that make up the union. So H is in AN for some AN in S. And to say H is in AN is equivalent to saying that H is a coset representative for AN. In other words, HN is equal to AN. And so that's equivalent to saying HN belongs to S. So this is the key property. H belongs to capital H if and only if HN belongs to S. Now we can show easily that H is a subgroup of G if we have two elements in capital H. Their cosets are in S by the key property, and S is a subgroup of the quotient group, so the inverse and the product of these two cosets is in S, and therefore, again by the key property, H inverse and HK belong to capital H. So capital H is indeed a subgroup of G. Also, N is the identity element of S, and so N is a subgroup of H. It belongs to S, and therefore it's one of the cosets in the union that makes up H. So it belongs to H as well. And finally, to see that S and H mod N are equal, if we take a coset in H mod N, little hn, then by the key property, actually by the definition of H mod N, little h belongs to H. By the key property, Hn is in S. So Hn is at least a subset of S. But for the converse, if An is in S, then the key property tells us that A is in capital H, and so An is in this quotient group. So that's the reverse inclusion, and then they are equal. So that takes care of the existence part of this theorem. As to the matter of uniqueness, if Hn equals Kn, then H will be equal to K. And here is the reason. if we take a little h in capital H, Hn belongs to the quotient group H mod n, which is now equal to K mod n. And so Hn is an element of K mod n, which means it's a coset of n with representative from K. If we take n equals 1 here, we'll get H, little h belongs to this coset Kn. But this is contained in K, capital K, because n is a subset of capital K and little k belongs to capital K. So anything in capital H is also in capital K. So H is a subset of K, but there's a symmetry here between H and K. So we can do this same argument with H and K reversed. They'd be equal. And the final part of this theorem, suppose that H mod n is normal in G mod n. We want to show H is normal in G. Well, for any little h in H and little a in the group, if we conjugate little h by a and use that as a coset representative for n, then the coset product tells us we can write it this way: an times hn times a inverse n. But H mod n is assumed to be normal in G mod n, and so this belongs to H mod n. This is the conjugate of the coset hn by the coset an. So it still belongs to H mod n. And therefore, AHA inverse belongs to H. So H is closed under conjugation, it's normal. So that completes the proof. Now we can show that every finite abelian group is Lagrangian. So let G be an abelian group of order n. And then we're going to use this inductive argument that we've discussed before. So we're going to proceed by induction on n. When n is 1, the result is clear. So assume that it holds for abelian groups of order less than n and bigger than or equal to 2, and let G be an abelian group of order n. Now, the simplest, perhaps the simplest way to prove this is, suppose that we have D a positive divisor of n. We want to show that G has a subgroup of order D. If P is a prime dividing D, this divisor, it will also therefore divide n, of course. So Cauchy's theorem implies that G has a subgroup, H sub P of order P. And then we can take the quotient group, and that has order n over P. Therefore, the inductive hypothesis implies that G mod HP is Lagrangian. And since, D was a divisor, P was a divisor of D, so D mod P is an integer. It divides n mod P. I should say D over P divides n over P. So it follows that this quotient group has a subgroup of order D over P, because the quotient group is Lagrangian. And then we apply the theorem 9.4, which tells us that G has a subgroup, HD, for which this subgroup is the quotient group HD mod HP. The subscripts here are indicating the order. The order of HD is the order of HP times the order of SD over P from this formula, and that's equal to D. So G does in fact have a subgroup of order D, and that's what we wanted to show. Okay, so finite abelian groups are Lagrangian. What about finite P groups? Why are they Lagrangian? Not only are they Lagrangian, but if D is a positive divisor of the order of G, then G not only has a subgroup of order D, but it actually has a normal subgroup of order D, and that's pretty significant. So let's prove that. I don't know that there's a term for that, so for the purposes of this proof, I'll just refer to that as normal Lagrangian. Okay. So we'll proceed by induction on n here. It's the exponent. The order of G is a power of P, because we're dealing with a P group. So we'll do this by induction on n. If n equals 1, G has order P. It's a cyclic group. The only divisors of the order of G are 1 and P, and G certainly has a normal subgroup of order 1, the trivial subgroup, and the full group is the normal subgroup of order P. So G is normal Lagrangian when n is 1. So now let's assume that any P group of size P to the n, where n is less than m, is normal Lagrangian. And let the order of G be P to the n. Well, a theorem from the previous chapter tells us that the center of a P group is non-trivial. So it will have order, I'm just going to call it Z, it will have order P to the Z, where Z is at least 1. And so the order of G is P to the n. It's the product of the order of G mod Z and the order of Z, and that's equal P to the Z, order of G mod Z. So the order of this quotient group is P to the n minus Z. Well, n minus Z is less than n, so the inductive hypothesis tells us that G mod Z is normal Lagrangian. It has a normal subgroup, S sub k, of every order P sub k, where k now is ranging from 1 to n minus Z, because that's the order of the group we're dealing with. And then Theorem 924 tells us that there is therefore a normal subgroup, HK, of G, for which the subgroup of the quotient group has this form. And as we've done before, compute the order of the numerator here. It is P to the Z plus K. So it follows that G has a normal subgroup, HK, of every order P to the M, where M is between Z and N. It's of the form Z plus K, where K ranges, have it back here, from 1 to n minus Z. Let's see, Z plus 1. Okay, so I add Z to this range. We go from z plus 1 to n. But z, which is the center of the group, is a finite abelian group, and so it has, by what we proved earlier, it has a normal subgroup of every order p to the m, where m goes from 1 to the order of the center, which is z, p to the z. Okay. So also, these subgroups are normal in G because they belong to the center. Okay. Just because they're normal in a subgroup, an arbitrary subgroup, doesn't mean they're normal in the full group. But when the subgroup is the center, it means that anything in the center commutes with everything in the group. So these subgroups will be normal in G itself. And so when we piece these two ranges together, we go from 1 to n. So G has a normal subgroup of every order p to the m for m ranging from 1 to n.